Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 1, Section 2, Chapter 3, Topic 4, Frequency Domain.
Exploring the frequency domain in semiconductor packaging.
Introduction.
The frequency domain is a fundamental concept in electrical engineering that describes the behavior of signals and systems in terms of their frequency components. In semiconductor packaging, understanding the frequency domain is essential for analyzing and optimizing electrical performance, signal integrity, and electromagnetic compatibility of integrated circuits, ICs, and electronic systems. This overview aims to provide a comprehensive understanding of the frequency domain and its applications in semiconductor packaging, covering its principles, characteristics, analysis techniques, and significance in electronic design.
Principles of the frequency domain.
The frequency domain represents signals and systems in terms of their frequency content, amplitude, and phase relationships, rather than their time domain waveform. The key principles of the frequency domain include: 1. Fourier transform. The Fourier transform is a mathematical technique used to decompose a time domain signal into its constituent frequency components. It transforms a signal from the time domain to the frequency domain, allowing engineers to analyze the signal's frequency content and spectral characteristics.
2. Frequency spectrum.
The frequency spectrum of a signal represents the distribution of its frequency components and their corresponding magnitudes and phases. It provides insights into the signal's spectral content, bandwidth, and harmonic distortion, facilitating analysis and characterization of signals in the frequency domain.
3. Frequency response. The frequency response of a system describes its behavior in response to sinusoidal input signals of different frequencies.
It quantifies how the system amplifies, attenuates, or phase shifts input signals at various frequencies, providing valuable information about system performance and stability.
Characteristics of signals in the frequency domain.
Signals in the frequency domain exhibit several characteristics that are crucial for understanding their behavior and analyzing their spectral content. 1. Frequency components. Signals in the frequency domain consist of various frequency components, each representing a sinusoidal waveform at a specific frequency. These frequency components contribute to the overall spectral content of the signal and determine its frequency response characteristics. 2. Amplitude spectrum. The amplitude spectrum of a signal represents the magnitudes of its frequency components, indicating the strength or power of each frequency component relative to others. It helps identify dominant frequencies, harmonic distortion, and signal-to-noise ratio (SNR) in the signal.
3. Phase spectrum. The phase spectrum of a signal represents the phase shifts of its frequency components relative to a reference signal. It provides information about the time delays and phase relationships between different frequency components, influencing signal alignment and coherence in the frequency domain. Applications of the frequency domain in semiconductor packaging.
The frequency domain has various applications in semiconductor packaging, enabling engineers to analyze, optimize, and validate electrical performance, signal integrity, and EMC of semiconductor devices and systems. 1. Signal integrity analysis. In semiconductor packaging, signal integrity analysis involves assessing the quality and integrity of electrical signals transmitted through interconnects, traces, and package substrates. By analyzing signals in the frequency domain, engineers can identify signal distortion, jitter, and noise, and optimize signal routing, termination, and equalization techniques to improve signal integrity and minimize data errors. 2. Power integrity analysis. Power integrity analysis focuses on evaluating the distribution and delivery of power within semiconductor packages, ensuring stable and efficient power supply to ICs and electronic components. By analyzing power delivery networks (PDNs) in the frequency domain, engineers can assess impedance profiles, resonance effects, and voltage ripple, and optimize decoupling capacitor placement, routing, and sizing to enhance power integrity and minimize voltage noise.
3. Electromagnetic compatibility (EMC) analysis. EMC analysis involves assessing the susceptibility of semiconductor packages to electromagnetic interference (EMI) and their ability to mitigate EMI emissions, ensuring compliance with regulatory standards and preventing interference with other electronic devices and systems. By analyzing electromagnetic fields and radiation patterns in the frequency domain, engineers can identify resonant frequencies, coupling mechanisms, and shielding effectiveness, and optimize package design, grounding, and filtering techniques to enhance EMC performance and minimize EMI emissions. 4. Signal processing and filtering. In semiconductor packaging, signal processing and filtering techniques are used to enhance signal quality, remove unwanted noise, and extract relevant information from signals.
By applying Fourier transform and frequency domain filtering algorithms, engineers can analyze signal spectra, suppress interference, and extract desired frequency components, enabling advanced signal processing and communication techniques in semiconductor devices and systems.
Conclusion.
In conclusion, the frequency domain is a fundamental concept in semiconductor packaging that plays a critical role in analyzing, optimizing, and validating electrical performance, signal integrity, and EMC of integrated circuits and electronic systems. By understanding the principles, characteristics, and applications of the frequency domain, engineers can effectively analyze signals, assess system behavior, and design robust semiconductor packages that meet the stringent requirements of modern electronic applications. As semiconductor technology continues to advance, the frequency domain will remain indispensable for addressing emerging challenges and optimizing performance in semiconductor packaging.